Actually, light slows down as it travels into a more optically dense medium. Refractive index is a measure of this change in the speed of light. Now, for us to talk about this precisely and do calculations, we're going to need to know the speed of light when there's no optical density. That is, the speed of light in a vacuum. Modern SI defines the speed of light to be 299,792,458 metres per second. We will normally, however, just approximate this to 3 by 10 to the 8 metres per second. That's a perfectly good approximation. It's 3 by 10 to the 8 to 4 significant figures over here. So 3 by 10 to the 8 is a perfectly good approximation. But that precise number, 299,792,458, is a definition in SI units. It has to do with actually the definition of the second. So that's the speed of light in a vacuum. Absolute refractive index is the ratio of the speed of light in a vacuum, that's C, to the speed of light in that particular material. That's the absolute refractive index. It describes how much slower light is. Here's a table of some typical refractive indices. You won't need to know these, this whole table. We'll provide what you need, but you will probably get used to some of these numbers because you'll use them a lot in calculations. So, air is very close to a vacuum. Light travels pretty much the same speed, 3 by 10 to the 8 metres per second, through air. So the refractive index of air is 1, same speed. But water, for example, light slows down to 2.26 by 10 to the 8 metres per second, which gives it an absolute refractive index, it gives water an absolute refractive index of 1.33, and so on. But for us to use the concept of refractive index to actually calculate angles with Snell's law, we need something called the relative refractive index. The relative refractive index for light travelling from one material to another is the ratio of the absolute refractive indices of the two materials. And it's defined like this. The relative refractive index going from material 1 into material 2 is the refractive index of material 2 divided by the refractive index of material 1. The new material's refractive index divided by the old. Because absolute refractive index has the speed of light in that material on the bottom of the fraction, this means that the relative refractive index, material 2 over material 1, new material over old, is also equal to the speed of light in the old material over the speed of light in the new material. Be careful about which way that goes. And then we get to Snell's law. Snell's law can be written two different ways. One way is to say the refractive index, the relative refractive index, going from 1 to 2 is the sine of the angle in material 1 over the sine of the angle in material 2. But if you write this one out as n2 over n1 and then cross multiply, you'll see that you can also write this same rule as n1 sine theta 1 equals n2 sine theta 2. Now, if you're not comfortable with 1 and 2, you can also write this with I and R, incidence refraction. Relative refractive index going from the incident material to the refracted material is the absolute refractive index in the new material, the refracted material, over that of the incident material. It's hard to say all this. And Snell's law you can write as Ni sine I is Nr sine R, where this is the angle of incidence, this is the angle of refraction. The advantage of doing it this way with 1 and 2 is that if you end up in a situation where you're going from one material to another, you can just go n1 sine theta 1 is n2 sine theta 2 is n3 sine theta 3 is n4 sine theta 4 and just keep going.